Okay, in this video, we're going to talk about chapter 5 in our textbook, which is divide and conquer. So again, we saw a little bit of this in chapter 4, and that this is the divide by a constant factor in essence. Okay, so we're just going to continue on in that vein. So it starts off here in the book. We're talking about that. Here's the general way this works. So you have a problem. You're going to divide the problem up into subprograms of the same size, ideally of equal size. Okay, then you're going to solve each of these using either the same algorithm recursively, or sometimes you'll use a different algorithm. And then at some point, in most cases, you have to combine those answers back together, or at least find the answer among the subproblems. Okay, so this turns out to be a pretty efficient way. It's the most common thing we think of in problem solving techniques. Okay, so here's a diagram here. So you have the problem of size n, then you have two subprograms that are approximately the size of n divided by 2. You then get the two solutions. You then bring them back together in order to find the solution to the whole problem. Okay, so they give an interesting example here. What if we were going to take the sum of n numbers, a0 through a to n minus 1? Okay, so as long as n is bigger than 1, we can divide this up into two instances of the same problems. Same problem. We're going to take the first half, add those together, the second half, and add those together. Okay, so that's a divide and conquer. We've divided the problem into n divided by 2, roughly, steps. We're going to then put them together. So the question then is this more efficient than the brute force? Okay, and it turns out that it's not. You're still doing the same number of additions. Okay, in fact, you're adding time to it by having to take the time to split them up. Okay, so not all divide and conquer are more effective. Okay, but a lot of them are going to be. So we have here some formulas here that are going to help us out. Okay, so the first one we're talking about here is this formula here, this formula 5.1. Okay, so what this is saying is that the total time it's going to take us to do n. Okay, we're going to divide up our problem into a pieces, each of which, wait, let me start over again. A is the number of pieces we break it into. That's it. And B is the size of each of those. Okay, so we need to solve A problems now that are n divided by B in size. That's it. Okay, so that's just what it's going to take. You know, if it takes this long for n, then it's going to take this t n b to solve each sub problem. There are a of those, so that's the time. Okay, and then we have to add in a function that is going to be the time to divide the instance up and then put it back together. Okay, so this is called the general divide and conquer recurrence. Okay, so this order of growth for Tn is going to depend on A and B, right? Depending on what our problem is. Okay, and we're going to get from that this master theorem here. Okay, and it starts off with this assumption that if the f of n, so if this function here, so if the assembly and disassembly part of this, okay, is in big theta, so if it's exactly n to the d, okay, where d is greater than or equal to 0, so constant time it would be equal to 0. If not, it's going to be equal to something else. Okay, then in this recurrence relation up here that we just did, okay, then we can look at the t of n and look at how a relates to b to the d. Okay, so if we're looking at n squared, then we would take our b, which is the size of each chunk, squared, okay, and see if our a is less than that, or equal to that, or greater than that. Okay, and depending on this, the relationship between these two numbers, then we're going to get our t of n being in one of these three categories. Okay, so which can come in handy for us. Okay, so this gets us to our first sort that's worth knowing. Okay, in fact, we're going to get the two major sorts that we do most of the time in this chapter. The first one's merge sort, the other one's quick sort. Okay, so with merge sort, it is the very definition of what we do with divide and conquer. okay? And it turns out to be a lot more effective than you may think, okay? So we're going to talk about it in words first, and we'll get to the algorithm. So the idea here is that we're going to take an array that we want to sort. We're going to divide it in half, and then recursively sort each half, okay? We're then going to divide it in half again, okay, and divide it in half again, all the way down until we have one element sets or one element arrays, okay? We're then going to compare those one element arrays, that's the merge part, to merge them back together, okay? So here's the definition in pseudocode here, okay, on page 172. So we want to sort this array from 0 to n minus 1 by recursive merge sort. There's our input. This is, and again, it's important, these are orderable, okay? You can't really sort an array of cats unless you have a way to determine whether one cat is greater than the other or not, okay? And then our output's going to be an array of the same size, but it's going to be sorted in non-decreasing order, okay? So again, we're assuming if n is greater than 1. If n is not greater than 1, then we don't need to sort because we only have one element, right? Okay. But this is the idea that we're going to first split them apart. Okay, so that's what starts this first line. We're going to copy from the floor of n divided by 2 minus 1, okay, to b. We're going to copy the last half from that midpoint on, okay, to c, okay. We're then going to merge sort each half. Then we're going to merge those back together. So when we're done, okay, from this first call, however, if we had 10 elements in A, then B has 5 elements and C has 5 elements, okay? When we're back to this point after our recursive calls, those two are now sorted, okay? And then we're going to merge them together, okay? And at this point, I think it makes sense maybe to do a picture of this. So let me switch to the iPad. Okay, I'm going to stop the video just for a second while I'm doing that. Okay, so now we have the iPad up. We should be able to do this a little better here. Okay, so the idea again. Okay, so if we have some numbers, whatever they are, let's say we've got 5, 2, 13, 4, 7, 12. Okay, so we've got 6 numbers. Okay, we put them all in a box like this. Okay, we start by dividing them into half. Okay, so that divides into 5, 2, 13. That's the B in our example. 4, 7, 12. Okay. Our base case is when we have 1. Okay, so we need to do it again. So we divide this up into 5, 2, and this one just into 13. Okay, we divide this one up into 4, 7, and then a 12. We divide this one up further into a 5, and a 2. Okay, so these connect to make it clear. Okay, and this divides up into a 4 and a 7. Okay, so now we have to start merging them back together. Okay, and these are in recursive calls, so these are all happening at one time. Okay, so we start the merge, and I wish I had more screen here. The 5 and the 2. Okay, of these two, you're going to pick the smaller. Okay, so you put the 2 there, then you put the 5. Okay, you're now going to compare this with the 13. Okay, and build up a 2, 5, 13. Okay, same thing over here, the 4 and the 7. Okay, you're going to combine those same order, 4, 7. You can combine that with the 12, and you're going to get the 4, 7, 12. Okay, then to create this first one, you're looking in particular at the first one here and the first one here, because these are both sorted. Okay, I'm going to have to wipe out some of this. to make some room and move to the top. Okay. So we have these two lists we're going to do the merge on. Okay. So as I'm putting them together, of the 2 and the 4, the 2 is the smallest. So I put the 2 here, wipe that out there. The pointer now moves to here. I now compare these two, and the 4 is the smallest. Okay. So I'll wipe out the 4, move the pointer to there. Of the 2 that are in position here, the 5 is the smallest. Wipe it out. Okay. Then the 7, then the 12, and then the 13. Okay. And that's the basic idea. And one thing we'll see in the algorithm is that if one of these runs out, okay, so if we still had in one of them, you know, a 19, 25, 30, okay, all of these are going to go at the end because they're sorted. We've gotten rid of everything smaller. Okay. So that's kind of the graphical overview of what this is going to look like. Okay. So let me see if I can get back to the other share. Okay. So that's the idea here. Okay. So that was the the merge sort. The merge comes in here. Okay. And again, we're looking at those positions and we're copying to our new sorted array. Okay. So in this case, we have the input is going to be the 2 arrays B and C. Then the output is going to be the sorted array A. Okay. And then again, we're going to go through the loop here and we're doing just what I said, where we're taking that whichever element's the smallest. Okay. So if the positions that we're at currently, we start at 0, whichever one's smallest, we're moving that to, we've got a K counter going for A, else, okay, we're moving the other one over, then we're increasing K going forward. Okay. And then here's if I is equal to P. So if we end up with one element or one of the 2 that's empty and the other one's not, okay, then if those pointers kind of cross over, then we're going to copy just the rest of them. Okay. So again, here's an illustration, and a little better, I guess, than I worked it out, but the same basic idea that we start with these numbers, we divide it, we divide it, we divide it. In this case, it divided evenly. Okay. We then combine those back together to get what we're working on here, get the sorted total. Okay. So when you think about, is that quicker than a brute force algorithm that we've done, such as select sort? It's a better of those. And it turns out that it is. And it goes through figuring this out, but we're not going to do this math anymore, just to understand that we're getting here in the worst case scenario with an n log n. Okay. And if you remember, selection sort was an n squared, and n log n is better than n squared. Okay. So this is a better algorithm for sure. Okay. So that's the first section. Okay. And I'll post some homework problems at some point. So we now get to quicksort. Quicksort is the other important algorithm based on divide and conquer. Okay. And when you're looking at the 2, it really comes down to merge sort is overall going to be more effective most of the time, but quicksort, depending on how things sort out, could be a little bit quicker. So, but they're both good. They're both fine algorithms. I think people tend to go with merge sort because it's easier conceptually, but quicksort's a little bit different. Okay, so here's the idea behind quicksort. Okay, so here's our algorithm here. We're going to sort a subarray by quicksort. We have, again, array A coming in, and the output is going to be the same thing, but sorted. Okay, and we're going to do this time by first partitioning. Okay, based on some S. And picking this S can be a tricky thing. Okay, we're then going to do a quicksort on each half of that. Okay, so rather than dividing it in half like merge sort does, we're going to do a a partition like we talked about before, okay? And we could use the Lamuto, which we talked about before. That's the one where you have the S and the I, okay? And it's probably, well, I'll do this other one instead. So I'm not sure that we were 100% clear on that before, at least everybody. So we'll talk about this idea of partitioning, okay? Again, the reason we partition is because it's quicker than doing a full sort, okay? And this is going to take advantage of that. But instead of the Lamuto, which again, as we talked about, only goes from the left, we're going to do this other one that was suggested by the CAR Hoare, who is a really prominent British computer scientist. You see his name a lot. He also had, seems like a son or something, Tony Hoare, who's still around. I think at least he was fairly recently. That's also prominent. Anyway, so the idea here is just like the Lamuto, but instead of just going from the left, looking for items that are smaller, it also goes from the right. Okay, so it can be more effective in that way. Okay, so as we go down and take a look at this, this is the idea that we get. Okay, that we're going from some point, moving in both directions with an I and a J. Okay. And let's see if it has an example. It may not. I mean, it's work one. Yeah, here's one. Okay. So with this example, you can see that the initial conditions are, we're still taking the first element. There we go. We're taking the first element to be our pivot point. Our I is being set to the first position after that, or the one position. The J is at the end. Okay. We're then going to move I over as far as we can. Remember, 5 is going to be in the middle, so we want to keep everything that is smaller than I to the left. Sorry, smaller than your pivot point, smaller than P, over here. Okay, so we're going to go 3 is smaller, we're good. 1 is smaller, we're good. 9 is not, so we stop. So I stops in this position. At the same time, we're taking J from the end, and we want these to be bigger than P. So 7 is, but this one's not, 4 is not, okay? We're then going to swap these out, okay? We're now going to move forward. Oh, we hit another problem. I is an issue there, okay? We're here at 9, we move to here. Okay, now we're at a standstill, okay? So we move I until we find one bigger, we move J until we find one smaller. We then swap those, okay? We swap those here, okay? Once we've swapped them, we see that I and J are going to cross. We're looking for that. So at this point, we're going to move what was pointed to at I, okay, which is the last element smaller than P. J and I cross each other. It's now J and I. That's how we know we've reached the end, okay? So we're now going to move the pivot to where the J was, swap it around. So the 2 moves to the front, okay? So now that we've done that, we're going to do this again on the half, right? It's a recursive, okay? So we're going to take this 2, do the same thing, okay, till we get the sort here, okay? And then we know those are going to be okay. So now we do the 3 and the 4, and then we do the 8, 9, 7, and so forth, okay? So that's the basic idea of that. It's this, that we're moving from both ends at the same time, okay, to do the sorts, okay? And then we can actually go up and look at the actual code here, okay? So again, we're just going to set our pivot point every time we call this recursive algorithm to be equal to the initial element. There are other ways you can set that may be more efficient, but this we're taking here, that's A to the L, the left, okay? And then we're also setting the I equal to that left, and the J is equal to R plus 1, okay, to put us at that far right position, okay? So we're then going to just do this repeat. We're looking for the I, okay, until we get one that's bigger here. We're then looking for the J moving at left, so the minus, till we get one that's smaller. We're then swapping those. Okay, we're going to do that until I and J flip. Okay, once we do that, then we're going to swap those positions. Okay, and then we're going to return our position for J. Okay, so that's the partition that we're going to do. What it looks like, again, it's like the other, it's like Lamuto, except we're going from both ends. Okay, then we should get down. Oh, I guess we had the algorithm for that before. That I probably skipped over. Yeah. Well, yeah, we talked about that. We're just going to partition it and then quick sort each half. So that's how that one's going to work. Okay. And there are different strategies on how to pick that pivot point. Okay. So for example, here it talks about there's the randomized quicksort that uses a random element to be the pivot point instead of the first one. There's this median of 3 that'll take leftmost, rightmost, middle element, get their median, and make that the pivot point, and different things that we can do. Okay. There's also some modifications here that we're going to switch to the insertion sort, which we talked about last chapter. If there's not very many elements, okay. So that would certainly speed things up a little bit, okay, in those cases, okay. So it does have a weakness. We haven't talked much about stable sorting algorithms, but it does mention in the book, a stable sorting algorithm is one where if you have 2 elements that are the same in an array, the sort keeps them in the same relative position. So if you have a 3 that appears in position 5 and a 3 that appears in position 10, then once they're sorted, the 3 that was in position 5 still occurs before the 1 in 10. And it's not a big deal in smaller cases, but if it's on bigger cases, then it can become a problem that you're moving things around more than you need to. Okay, so that's something we talk about. Okay, so that's one of the issues that we have to worry about. Okay, and it's also a problem that choosing the pivot can happen in kind of bad ways. Okay, so that's really the other issue you have to worry about. So it's not guaranteed to be faster than merge sort, but it can be. Okay, and it still comes down into the n log n is where we're at. Okay, and you see here on the average we're at basically n log n. Okay, because we ignore all the constants over here. Okay, so again, not a bad algorithm for sure. Okay, so section 5.3 talks about binary tree traversals. Remember, the binary tree is a tree. Binary meaning only has a left and a right child. And it's the case that the left is always smaller and the right is always bigger. The whole subtree to the left, everything is smaller than the current node. Okay. So there are a lot of algorithms based on this. And this one, there's a height algorithm. I think it's relatively straightforward. Okay, that if we get to an empty set, then we know we've gone 1 too far in determining the heights. We're do a -1 there. If not, we're going to take the height of the left tree and the height of the right tree. Okay, and then add a 1 for the level that we're on. And that, I mean, it talks about that a little bit, but I don't think that's going to give you too much trouble. Okay, some things that are important to know here, because they come up a lot, are the tree traversals, which you've probably seen somewhere before. And that's the pre-order traversal, where you visit the root. So you add the root. So a traversal here, you want to touch every element of the tree. Okay, so you will turn that into an array, your tree into an array, for example. Okay, probably worth doing a visual on these. That may be easier. Okay, so let me do that. So let me share this screen again. I have my iPad this time, so I don't have to use my mouse, which should make everybody happy. Okay, so our traversals. Okay, let me clear this out here. Go to the screen. So we have a tree, whatever we have. It doesn't matter if we have, this is from the book here, A, B, C, D, E, F, and G. Okay, and C goes to F that way, and D goes to G. Okay, the assumption again being that A is greater than B and D and E and G. Okay, but if we're doing a pre-order, So the pre-order is visit the root, visit the left, visit the right. Okay, starts with A. Okay, visit the left to B. Okay, when we visit B, actually, let me do this again. We start at A for pre-order. Okay, add A to the list. We visit that. Okay, we're then going to go to the left. When we visit this, whole new world here. So we're going to add B to our list. Okay, mark it as visited. Okay, we're then going to hit the left. So we visited the root. Okay, we're going to visit this root. Okay, so D goes here. Okay, we try to visit the left. There is none. We've already visited the root. So now we visit the right. Okay, we go this way. Okay, and visit that. Okay, so the G comes after the D. Okay, and then these recursive calls all end. So we go back up to B, where we visited the left. Now that call is activated again, and we visit the right to get the E. Sorry, wrong color ink. E. Okay, now we go all the way back up. There's no left or right there. All the way back up to the first call we made to the recursive from A to B. And now we visit the right. So we go to here. C gets added. Okay, we go to the left again. F gets added. And there's our pre-order traversal. Okay, and in a similar way, let me come back this up while we're talking. In a similar way, we also have the in order, which is going to be left, then right, then root. Okay, so on that one, we move before we visit. Okay, we do a left first, make that recursive call. Okay, when we get to B, we don't visit it, we make a left again. Okay, when that's possible. Okay, so we've made the left, There's no left from D, so the first thing we visit is going to be D. Okay, so we visit D. Okay, so we do a left, then a visit, then a right. Okay, so after we visit that, we then go here. Okay, we try left, we don't, then we visit. So G becomes next. Okay, and then we'll just keep working backwards from there. Okay, and the book shows those, but I wanted to give you a little bit of an idea. Okay, not to waste all your time. So let's go back and do the last one. Okay, so that was the in order. Okay, with the in order, so with the pre-order, the root is the first in the element. With the in order, the root is kind of in the middle, and with the post order, the root is last. Okay, so the post order, and I think I didn't change that label in the other one, but you get the idea. So the post order, if my pencil wants to work, and I can spell. Okay, the post order goes left, right, and then root. Okay, so in that case, we start at A, but we go left, we try to go left, we can't, we go right, and then we visit. Okay, so in this case, the first element visited is G. So we start with G. Okay, and that's how those work. So if that's causing you difficulties, I'm sure there's lots of examples of that out there. Okay, so anyway, that should take care of that problem. Okay, so let me now, managing technology is always a fun task. Okay, so that's those things. Let me share the screen again here. That's what this stuff comes down to. Okay, and that was 5.3. So the next section, we're just going to cover half of this. I think the half will be enough for us. Okay. Okay, so yeah, we're going to do the multiplication of large integer part. Okay, but not the matrix multiplication. Okay, And this is an interesting thing here. And if you're especially if you teach high school, this is something you may want to go with your kids. It's an interesting concept. It's the idea here that there may be a quicker way than we normally use to multiply integers together. Okay, so the way we do it is by dividing them up into their powers of 10 and then multiplying those factors one time rather than having to do them all separately. Okay, so it saves some of the backtracking. Okay, so it gets into a formula that looks like this here, that if C is equal to A times B, then we're going to put that as C2, which we're going to calculate down here, times 10 to the second power plus C1 times 10 to the first power plus C0 times 10 to the 0th power, which is just 1. Okay, where C is going to be the product of the first two digits. C2 is the first two digits. C0 is a product of the second two digits. And then C1 becomes A1 plus A0 times B1 plus B0 minus the C2 plus C0 that we've just calculated. Okay, so we can generalize that, of course, to an N, which comes in here. Okay, where we calculate these guys down here. Okay, so it's an interesting thing. Okay, and it turns out that it is a little bit quicker. Okay, which is interesting. Okay, so what we're not going to do is the Strawson's matrix multiplication. It's the same basic idea, but I think this chapter is long enough, so we're not going to worry about that. You can look at it if you like, but I'm not going to ask you anything about it. Okay, and there's the homework. Okay, now we get to our old friend that I like, the closest pair and the convex hull problem. Okay, and again, we're in the divide and conquer phase. Okay, so let's start with the closest pair. If you remember the closest pair, you have a set of P points that you've put on the Cartesian plane. And we're going to assume that they're distinct just to avoid cases we don't have to worry about. Okay. We're also going to assume that they're in non-decreasing order of their X coordinate. Okay. And if not, we could just sort them, okay, to make this work. So the idea here is that you have this whole giant field of points. Okay. So let me, again, I think I could probably switch this up a little bit better, maybe, or write this up. If I can get all my pieces to work. Okay, so let me go to here. Okay, the idea being we have basically points that are all over the place. So the general concept is rather than trying from every point to every other point, okay? So for example, this point and this point are never going to be the closest point. I mean, they're just not, okay? So to kind of localize that, we're going to try to find, again, we know that they're sorted by X. We're going to find some middle between the points. And it looks like in my point, the middle may be somewhere in here. Okay. And we're going to divide it into two sections, okay? And these two sections, because we're dividing them the way we are going to have roughly the same number of points, okay? We're then going to check all these points against each other, okay, until we come up with the smallest point. So the smallest is closest distance. So the smallest distance in our section 1 and our section 2, okay, is that going to be the closest 2 points? Well, maybe. So let's say we get that as equal to D, and whichever one, and it's hard to say here which one's the closest. Let's just say, for instance, that this is our D. That's our smallest point. Okay. The smallest point over here turns out is bigger than that. Okay. So we have our smallest of these two subgroupings, but we now have to go through and we have to put in a strip on either side of this that is 2D wide. Okay. So D here and D here. Okay. And what you're concerned with there, that won't make the rest of my D. There we go. What you're concerned with there. So let's take a close up of that. Okay. So again, you've got a bunch of points over there. a bunch of points over there, okay? And if you got this one and this one being the closest, and this one, that one, okay? So there's one there. Now, let's say there's one right there, okay? So this is our D because it's the smallest, okay? But this crosses the boundary between the two is smaller than their D. So we're gonna have to check for that, okay? And that's basically all this is going to do. That's the idea, okay? So let's go back to the textbook to see what that looks like. So that's the idea. Again, they're showing it here that we're dividing things up. We're finding this middle point. We're looking at which one are the smallest of the two. We're then looking at those that are in this gutter that we form, okay? And that's basic idea behind that. And there's our more efficient closest pair problem and how that works out as far as an algorithm goes, okay? Then the convex hull, okay, remember the convex hull, we're trying to get the lines that make the smallest containing shape, basically, I guess is the way you could say that, okay? So let's look at how this one's going to work. Let's just switching back and forth today. Nope, that's not what I want. That's not what I want. That's not what I want. What do I want? That's what I want. There we go. Okay. So the idea of the convex hull, again, you've got some points. We're also going to assume they're distinct. We're also going to assume, I mean, they could be on the axis, doesn't matter where they are. Whatever points you have, okay? Okay, so we're going to start with the assumption that the points that are furthest to the left and furthest to the right are extreme points. And that's easy enough to prove, right? We know that this point has to be in our convex hull. If not, it would extend past it, okay? Same thing over here. So we have our two extreme points, okay? We're going to start by drawing a line between those, okay? Things that are to the left of that line, so if you're traveling on the line, the left up here, we're going to call this the upper hull. And the things that are below this, we're going to call the lower hull. And the book just deals with the upper hull because we're going to create them the same way, okay? And the way we create it, we're going to look, and I've got to get a better point here. We're going to identify a point, which we're going to call P max, which is the line the furthest away from this line that we created, okay? So if we call this P1, I forget what they call it, P2. This line P1, P2, the point that's furthest away, we're going to call P max, okay? And you can also argue fairly convincingly that P max has to be, not convincingly, easily, because it's 100% true, that P max has to be in the convex hull, okay? So you're then going to go through and make a line here, okay? So we now have 3 points in the convex hull. You now have to do this again, find a new P max recursively. So if this becomes a P max, okay, then the final hull is going to have that and that. If this becomes a P max on this side, your final hull is going to have that, okay? And that's the basic idea behind how that's going to work, okay? So let's go back and look at the textbook. Okay, so again, that's the convex hull problem. That's just what they showed us there. They're going to go through, determine the P max, and see if that is going to work out for us. Okay. Okay, and that's it for this chapter. I mean, this is a relatively long video because there's a lot here, but I should be putting up the problem set within a day or two. So if you have any questions, as always, let me know. We'll do our normal meeting on Thursday. If you have questions beforehand, especially if you can't make it, go ahead and make sure that you post those to the discussion board.